Today we are going to cover golden section search, which is an optimization technique, and we're going to be using it to find minimums. And we had looked at something very similar yesterday that we called not golden section search, but I'm going to start it off kind of the same way here, and then we'll turn this into golden section search. Okay. So here's the idea, is you've bounded your minimum, like we have done here, between x lower and x upper. And then from here, we're going to compute two other things. We're going to compute an x1, which is going to come from x lower. Okay. But it's going to be x lower plus some constant times the length of the interval. And let's do x upper minus x lower. Okay. And we'll want this number here to be something that's less than 1. That way, when we do compute x1, we actually end up somewhere in between x lower and x upper. Okay. And so let's just say, for instance, that maybe this puts us, how about, let's go right here. Okay. And because this one came from x lower, we're going to call it x1, which is going to be confusing because our x2 is going to be over here. But x2 will be calculated very similarly. x2 is equal to x upper minus d times x upper minus x lower. Okay. And so that might put us somewhere like, let's see, I'm just trying to make this look symmetric. I think about right here. Okay. And is what we can see here is the function value here at x2 is smaller than the one at x1. Okay, and so just like yesterday, is what this tells us is that the maximum, the minimum does not occur in this interval, and we can just ignore it now. Okay. So you can see we've actually cut out a pretty good chunk of this interval. Okay. And is what we want to do next is we're going to drop down and we're going to make some reassignments. Okay. So this x2, maybe even make a number line. That might be nice. And actually, better yet, I'm going to make that number line the right size too. Let's say right here. This is our new interval length. And so what this tells us is that x2 is now going to become the x lower. Okay. It also tells us that x upper will stay as x upper. I'll put some tick marks here. And then you'd think that we'd have to recalculate our x1 and x2 again like we did yesterday. And so it ends up that we're going to choose this value d here, or k, whatever you want to call it. We're going to choose this number, and how about we do change it to k, because I don't want us to mix this up with d, which will be something else in our code here later. Okay. We want to choose this value k so that x1 here becomes the new x2. Okay. So in other words, we no longer have to make this calculation for one of these. Okay. We still will need to make our calculation for x1. Okay. And one thing you will notice is that our x2 here is not quite where we would actually want it to be on the number line, because you could imagine if we were to compute x1, we would picture it maybe somewhere right in here, and we would have pictured that maybe x2 should have been somewhere right in here based on our previous picture. Okay. And this is because in this picture here, I haven't chosen the proper value for k here. Again, this looks like I probably chose maybe 0.75 for k. Okay, meaning that x2 is 0.75 of the length of the interval over from x upper, and x1 is about 3/4 the length of the interval from x lower. Okay, and this is not, again, this is actually not the value of k we want. Okay, but we are going to figure this out. We're going to figure out what k will result in being able to assign x1 to be x2 down here in the next step. Okay, because again, this is going to cut out a calculation. Okay, this is going to make our code a little more efficient. So let's start setting that up. All right, so what we're going to do here now is we're going to set up a couple equations. Okay. Maybe I should switch colors here. Let's see. Switch to blue. All right, so let's actually write down one of the equations we already had, which was about x1, and we're going to actually write two equations here about x1. Okay, one of these, again, is just the original, so x1 is equal to x lower plus k times x upper minus x lower. Okay, and now we're going to have another equation here for x1. Okay. Except for I want you to think about this x1 here as our x2 for a minute. Okay. So if we were going to be computing this x2 here, the idea is that we'd want to take x upper, which note hasn't changed. Okay. So I'm going to write in here x upper minus k. And then I want you to note how to compute the length of this pink interval. Well, it's x upper still, because x upper hasn't changed. But our x lower was equal to, or is equal to, our x2. Okay. So we have two ways of actually calculating x1 here if we're looking at both our first and second iterations of this technique. Okay. Well, there's our equations. Let's go ahead and set them equal to each other. Okay. And we'll actually eventually come up here and we'll use our equation for x2 at some point, because it will get in our way, but it's going to make things messy if we insert it right away. Okay. Let's go ahead and set these equal. So we have our x lower plus k times x upper minus x lower is equal to x upper minus k times x upper, and then double negative, so plus k times x2. And we'll keep going here. Let's, while we're at it, also distribute this k through, and then we'll make that replacement for x2 here in a second. So we have x lower plus k times x upper minus k times x lower is equal to x upper minus k times x upper, and then plus k times x2. Okay. And so x2 was equal to x upper minus k times, and actually, why don't we distribute that too while we're at it? So minus k x upper, and then plus k x lower. Okay. And I'll get this timer out of the way. All right, so it's looking a little messy, but we'll distribute one last time here, and we'll start to bring this together. So we have x. Actually, let's see if anything cancels right now so we don't have to write it down again. I actually don't see anything yet. So x lower plus k times x upper minus k times x lower is equal to x upper minus k x upper, and then I need to distribute this k through, so we're going to have a plus k x upper. So those will actually cancel. Maybe I'll just note that right now. That's kind of nice. And then we'll have, what do we have next? We'll have minus k squared x upper, and then plus k squared x lower. All right, and that looks good. Okay. And the question is, does anything else cancel? The answer to that looks like a no. So what we'll do now is let's start grouping everything together and see if we can do anything with this. See if we can actually solve for k. All right. So let's go ahead and we'll move these, everything that's on the right, we'll move it to the left. And I'm going to group them in a certain way here as well. So let's maybe say k squared. Okay, so k squared. There are two terms that'll have that. We'll have x upper, and we'll have this x lower. But if I'm moving it to the other side, it should switch signs. Okay, that looks good. Let's maybe just note to ourselves we've used up these two terms so that we don't accidentally use them again. We also have two k terms over here, so I'm going to say plus k. I'm just factoring out the k, x upper minus x lower. Okay, so that looks pretty good there now. And then we have this x upper here and x lower here. Well, if I were to add this over, I'll have x lower minus x upper. But notice that these are all x upper minus x lower. So we could just factor a negative out of those, and then we have our x upper minus x lower, and then all equal to 0. Okay. And now x upper minus x lower should always be a positive number. Okay? It should always be a positive number. It should never be 0. It should never be negative. But more importantly, it should never be 0. Okay? It should never be 0. So that means we can divide both sides of this equation by x upper minus x lower, resulting in a very simple equation. K squared plus k minus 1 equals 0. All right, and so this means that we're getting close to understanding why this is called golden section search. Okay. I realize that my OneNote name up here still says not golden section search, but we are looking at golden section search. Okay. All right, let's see here. Let's see if we can go a little further down. Okay. This is not one you're going to want to try and factor. We're going to want to go right into the quadratic formula. So we'll have k equals minus b plus or minus the square root of b squared, so it'll just be 1, minus 4ac, and c happens to be negative 1, and then this is all over 2a, okay, and a is just 1. A lot of 1's in here. Okay. And so this gives us minus 1 plus or minus the square root of 5, and then all over 2. All right. And the next thing to note here is that one of these values is going to be negative and the other one's going to be positive. Actually, these are both going to be, oh no, that's right. Yeah, one of these will be negative, one of these will be positive. So one of these is going to make sense and the other one's not going to. Okay. So is what we're really going to be looking at here for k is the minus 1 plus the square root of 5 over 2, okay, which happens to be what is called the golden ratio. Well, this is the golden ratio minus 1, okay, and I'll show you what the golden ratio is right here. So the golden ratio is actually oftentimes notated by phi, and it is 1 plus the square root of 5 over 2. And so if you were to subtract 1 from this, phi minus 1, we'll get this value k down here. So we'd have 1 plus the square root of 5 over 2. And again, I'm just subtracting 1. So this would give us minus 1 plus the square root of 5 over 2. Okay. So this value of k is related to the golden ratio. Okay. And again, this number here is going to allow us, to, when we go from one iteration to the next, one of these assignments will be automatic. We won't have to make the calculation. We won't have to do, in this case specifically, we won't have to do x2 is equal to x upper minus k times x upper, x upper minus x lower. It'll just be automatic. We'll just say, hey, x2 is going to be equal to x1. It's just an assignment, not a calculation. Okay. All right, now the next thing that we're going to want to look at that's going to be important here is we're going to want to know what's going on with the error. Okay. All right, so let's erase what we have here, and what we'll do is we'll start talking about the error. Okay, so I'm going to just get rid of some of this. But all this calculation we did here, the whole point is that we discovered that k here should just be the golden ratio minus 1. And if I can get this tool to work, which clearly I'm not. There we go. Then we can move on to that. There we go. I'm going to get rid of this here too. All right, almost there. And so what we're going to do real quickly is we're going to replace that k up there with phi minus 1, or the golden ratio minus 1. Okay. So x lower is equal to phi minus 1 times x upper minus x lower, and x upper minus phi minus 1 times x upper minus x lower will give us x2. Okay. And so now the question is what's our error? What's our error? So let's think about it this way. Okay. When we do perform this algorithm, okay, remember that what we're going to do to go from this step to this step is we're going to test the y values at x1 and at x2. Okay? And so whatever one becomes lower, or is lower, I should say, that's going to be our updated version for where the minimum occurs. So x1 right now is our best guess at what the minimum is. Okay. Even though we can see where the minimum is in our picture, okay, there's two possibilities for the furthest away that the actual minimum could be. Okay. It could be, right, that the minimum is actually really close to x2. Or it could be really close to x upper. The only place we know it's not right was in this interval over here between x lower and x2. Okay. So if we're going to be really extreme about this, let's consider if the actual were at x2 or at x upper. That's the furthest off we could be for our error. Okay. So let's start off with it being at x2. Okay. If we start off with that, okay, then that means we're off by whatever the difference is between x1 and x2. Okay. And we have an equation for both of these right up above, which is useful. So we'll have x lower plus phi minus 1 times x upper minus x lower. And I might need to move this over a little bit. Okay. And then we're going to do minus x2. So that'll be minus x upper. Okay. Minus x upper. And then plus phi minus 1 times x upper minus x lower. Okay. Looking good. And let's keep going here. But I do want to point out that this is our maximum possible error, x1 minus x2. Okay. Let's keep going. Okay. Well, I should say our maximum possible error is either x1 minus x2, or it's going to be x upper minus x1. And we're going to see which one of these is going to result in you know, something bigger. Okay. So if we keep going here, we have actually two terms that are exactly the same. We could actually add those two together. We could say 2 times phi minus 1 times x upper minus x lower. Right? We add like terms. And then we have plus x lower minus x upper. Okay. And let's say we wanted those to be in the same order. Let's say we wanted to have x upper minus x lower instead of x lower minus x upper. We could factor out a negative here. I should change this to x upper and this to x lower. Okay. And now you might notice that these two terms have a common factor of x upper minus x lower. And so we could go a little further. So if I pull out an x upper minus an x lower from this first term, we'll be left with a 2 phi minus 2. I'm going to just distribute the 2 phi minus 2. And from this term, we're just left with a minus 1. Okay. So what this really leaves us with is that the distance between x1 and x2 is really just x upper minus x lower times 2 phi minus 3. Okay. So there's one of our options. So we were saying that even though this x1 here is where we think the root is, it is possible that the root could be all the way over here near x2, or all the way over here near x upper. Okay. And so we just considered the case where the optimum x value is close to x2. Okay. So let's consider where that optimum value is close to x upper now. Okay. So if that's the case, our error is just the distance between these two, our maximum possible error, I should say. So I'm going to consider now x upper minus x1. Okay. And we can kind of do the same thing here. We can say, hey, we have x upper minus, and we can use what we have for x1. Okay. X1 is x lower, so we're going to have minus x lower. I'm going to just move this down a little bit. So minus x lower, okay, and then minus phi minus 1 times x upper minus x lower. Okay. And let's see, is there anything that we can do with this? Okay. And we see that we have an x upper and an x lower showing up here twice, so maybe we can factor that out. So let me just put parentheses around it so you can see it. But yeah, we have an x upper minus x lower here, and we have one in this term here. So we have x upper minus x lower. If I factor that out, that's going to leave me with a 1 from the first term, and then it's going to leave me with a minus phi. Let me write that phi a little bit nicer. Phi minus 1. And then next, we can distribute that negative and see what we're left with. So we have x upper minus x1 is equal to x upper minus x lower, and then times, and that's going to give us a negative phi there, isn't it? Okay, a minus phi, and then we'll also have a double negative, so we'll end up with 1 plus 1. So this is 2 minus phi here in the parentheses. Now, note these two errors that we just found. One of them is bigger than the other one, and it's not clear unless you go and compute it. But if we were to go in and compute which one's bigger, okay, and I'm talking really about what I've highlighted here, it actually ends up that 2 minus the golden ratio is larger than 2 times the golden ratio minus 3. Okay, so our maximum possible error actually ends up being this. Now, another question that we should address would be, well, how do we make this maximum error here be a useful stopping criterion for when we're working with an x opt, or the x that minimizes our function? How do we make this work well for those x values if they're really large and if they're really small, right? Because if we're working with really large numbers, then this maximum error here might not be quite as important for the maximum error to be something really, really small, okay? And if we do have really, really small numbers that we're working with for x opt, then a really small maximum error still might not be sufficient. Okay, so the way that we can normalize this, or make this so that this is kind of a good stopping criterion for x opt being large or small, is we could just take this and divide it by x opt. See, hey, what ratio do we get when we take our maximum possible error and divide it by x opt? Okay, and so I'll show you what that is going to look like. We are going to use, actually, in our function that we'll build for golden section search, and actually I'm going to just rewrite it in the notation we'll use in our code here. We'll have EA is equal to, we'll still have this 2 minus phi, but in absolute values, we're going to have x upper minus x lower. Okay, and assuming I didn't write anything else, this would be exactly the same as this formula up here. But what we'll do is we're going to divide what we have up here by x opt. Okay, and again, what we're really doing is we're seeing what percentage our error is, our maximum possible error, of x opt. And again, x opt is the x value that optimizes our function, or in our case, minimizes our function. All right, and so now we've addressed the golden ratio, how that is going to come into play here, and we've addressed how we're going to come up with our error, okay, or EA. So let's go on and we will code this tomorrow.